This video is about expectation of discrete random variables. We know expectation assign numbers to some random variables, right? It's a function from a subset of a collection of all random variables to numbers. So expected values of random variables, if they exist, are numbers. But how the expectation would link numbers to random variables? This video discusses the cases concerning discrete random variables. And here is the definition. The expectation, expected value, first moment, mean, average, they are all referring to the same thing of a discrete random variable x with the support x1, x2, x3. Here we list all the possible values taken by this random variable x in one increasing order. If exists, is defined by this formula. So the expectation of x is essentially a weighted sum of possible values taken by x, with the weights equal to the probability value of the event x equal to xi. This is defined by the PMF function of discrete random variable x, and we know for discrete random variables, both PMF function and CDF function would determine the distribution, right? So this expression can also be expressed in terms of the CDF function of x. Here, I use the delta fx xi to denote the difference between values fx evaluated at xi and the values of the CDF function evaluated at xi minus 1. According to the definition, we know it's essentially describe the difference in those probability values. And because we are ordering suppose we order the supports, the elements in the support set of discrete random variable x in an increasing order, we know the difference is essentially equal to the probability value of x equal to xi. Here we also denote fx x0. X0 is not in the support of x equal to 0, right? Then in the end, those two different expressions, they would mean the same value if the summation well defined. The reason I emphasize that if exists, because we know for summation of infinite series, sometimes the summation is not well defined, right? So indeed, for some random variables, for some discrete random variables, they don't have well-defined expectation value because the summation here is not finite. They don't converge to a number. Then we don't have a proper expectation for such random variables. Of course, if we only have finite possible values taken by x, then the expectation is always well-defined, right? And it can be written down in this way. So now it's a summation of finite terms, which is always well-defined. From the above formulas, we can see that first, expectation may not exist for some random variables. For example, in case of non-convergent series here, if this summation of infinite series diverge, then we don't have a proper expectation for those random variables. Second, an important observation is that we can see the expectation of random variables, of discrete random variables, essentially is defined based on either PMF or CDF. If two random variables, they have the same distributions, they would have the same expectations. If the expectation exists, of course. For example, we could consider this case. Suppose we're gonna throw a fair coin for one time and denote x as the indicator function, which only equals 1 if you have a head and 0 if you have a tail or bottom. And denote y as 1 minus x. Apparently y is not equal to x, right? And only equals 1 if you have a tail instead of head. But given we are throwing a fair coin, both x and y, they gonna follow the Bernoulli distribution with successful rate 0.5. So 0.5, you get a head, then it's a success for x, 0.5, you get a tail, it's a success, which for y would be equal to 1. X, y, they are not equal to each other, but they have the same distribution. And what are the expected value of x and expectation of y? They essentially all equal to 0.5. You can verify by the definition here, because expectation of either x and y, they are all equal to 0 times 0.5 plus 1 times 0.5, which will be equal to 0.5. So if you have random variables, if they have same distribution, they're gonna have same expectation. Now let's take a look at another example about expectation. Suppose we have 10 apples and there are 3 bad apples. We choose 3 apples at random without replacement. What is the number of bad apples that you would expect? You can pause the video here and think if you can try to figure it out yourself. Well, if we denote the number of bad apples we have as the random variable x, we know this random variable would follow a hypergeometric distribution with the following PMF functions. And the expectation of x, the expected value of x, the mean, the average, the first moment of x, we can easily derive by the definition. And you just plug in those probability values. So in the end, we will have the value. You can pause the video here and make an educated guess. The value is actually quite intuitive, which is equal to 3 times 3 over 10. We have 3 times, right? We're gonna choose 3 apples. There are 3 bad apples out of 10. This is the expected number of bad apples that we would get. Thank you for watching this video.